Dear students, now in my present lecture, I'll be talking about electrostatic potential energy and potential. This topic is quite similar to the gravitational potential energy and potential done by you in class 11th. The electrostatic potential energy is the energy stored by the charge Q while moving against an external electric field. When I talk about work done, it is known to us that it is force into displacement, or if the path or force is not a constant, then in such case we talk about dW is equal to F dot dx, or in this case it is work done is integral movement from A to B F external force dot dr. And if I say this is the external force which is required to move the charge against a field, means field is against this external force, and I can denote Fe and F external with a negative sign, and hence I have got minus integral A to B Fe dot dr. This is the expression for potential energy. Now let's take one small example when we are taking the field of a point charge. We have studied field of the point charge will be radially outward like this. I have taken only 3 lines just to represent as an example. Now a charge Q is brought inside the field. When I say inside the field, means it was actually outside the field initially. Outside means where field is not experienced by the charge, and that is known as infinite. So the charge is going from infinite and is entering into the field. The field due to the point charge is given as kq by r square. Hence, if I talk about force experienced by this charge will be Eq, and it is kq r square into this charge q. So dW is equal to minus Fe dot dr, as I have already explained earlier. It is same as the potential energy. This is the small potential energy when the displacement was very small as dr. Now again I will explain with the help of this diagram. If this point charge has been placed at the origin, these are the directions of the field, and along this field only if I consider as the direction or the orientation of r, means when the charge is entering inside, field is not uniform, and hence I have to talk about small path covered. That small path along the line, maybe it is opposite to the line, but it is along the line only, and hence we call that with the term dr. So let me consider this mathematical expression now. dW is equal to minus Fe dot dr, which is du. So u will be integral from infinity to that point. That point is within the field given as the position r. This minus sign coming from here, k q1 q2 k q upon r square dr. If I integrate, I get the expression u is equal to k q upon r. What we can observe is, now it has become a system of the two charges capital Q and small q, and hence this is the energy of the system. When the charge small q has been brought at a distance r from this capital Q, both the charges are positive, and hence this quantity is coming out to be positive. It says that the energy has to be stored. This positive value talks about the energy stored. But in place of moving from infinity to that point inside the field, if within the field itself it moves from A to B, then I will call the position vector for A as RA and B as RB. Now the same quantity in place of infinity to R, now it is RA to RB. only the limits are changing. So my expression comes out to be like this. So potential energy is KQQ 1 upon RB minus 1 upon RA. Now a doubt arises in the mind, should it be only along the field line? Can't it be any path? So I have taken the next set as the path is not directly in this direction, it is some random direction. So now I cannot call it as dr, now I will call it as dl, small path. Again I have taken small path dl because it's a total curvature. Any small element I can take as a straight line. So small element I have taken as dl. This dl can be resolved in two components, one component in this direction, another component in this direction. If I talk about this particular direction component, I called it again as dr, and this is normal to this, so I have considered it as dn. So this path can be resolved into two components, dr and dn, both are perpendicular to each other. Now there is a force, there will be work done. So I can represent that work in two parts, like dw1 as F dot dr. Here this dot we have just now seen is 180 degree. Field direction is in this way, path movement is in this direction, they are making 180 degree with each other, and hence theta has been taken as pi. And dw2 is the work done along the path dn, so let me call it as F dot dn. But now this force is along the field and this path is perpendicular to it, theta becomes 90 degree. And now if I talk about dw, in the first case dw1, this dot product has created this negative sign, cos 180 is minus 1, has made it minus. But dw2, this cos theta is cos 90, which made it equal to 0. dw2 has become 0. So the total work done will be dw1 plus dw2. This is contributing to the 0 work done. That means only work done is this. So we have got dw1 only as the work done in moving the particle, charged particle, in any path. So the expression for work done remains same as the initial one, minus KQQ upon r square into that is a dr, and integrating it we get exactly same expression. Very important to understand it here. What we have observed, this expression has been obtained by any path, whereas this expression was considered as movement along the field. As the two expressions same, that means whatever is the path followed, work done does not depend upon it. It depends upon only the initial and final positions. So whatever is the path followed, if I consider the work done to be KQQ 1 upon RB minus 1 upon RA, this work done depends upon the initial and final position of the charge, not on the path followed. Hence, such force or the field against which work is done is conservative force or conservative field. Hence, this field presently the consideration was of the electrostatic field, and hence I conclude that the electrostatic field is conservative in its nature. So we say electrostatic field is conservative. When the field is conservative, then work done depends on initial and final positions. So here I can give another conclusion, that if the path is a circular path and starting from one and ending also exactly at the same point, Maybe circular or maybe any way. It is closed. Initial and final positions become same. If the initial and final position become same, means RB and RA are same. Will cancel each other. That means work done will be 0. So the another conclusion of the conservative field is work done is 0 when the path is closed. Now, we all know whether it is work, whether it is energy, whether it is potential energy, their unit is joule, and dimensional formula remains same as the work ml2t minus 2, and work or potential energy is a scalar quantity. All these things I derived considering the field of a positive charge, and the entering charge is also positive, and the expression for potential energy has also come out to be positive, depending upon whatever is this, may be positive or negative. Otherwise, as far as charges are considered, it is positive. But if one is positive and another is negative, that means the two will have attraction. So there is no external force to do the work. There is no need of external force to do the work. Under their own attractive field, they can move. And hence, if there is a negative term, means the potential energy is negative, it is not actually stored. It was originally there in the system, and by movement that energy is being utilized. So it is negative over here. So one charge is positive, another charge is negative. Although it is a scalar quantity, potential energy can have positive, but it can have negative value depending upon what are the two charges. Here in the repulsive field, the work was done. So there has to be some external source to do the work. That extra work is being stored in the energy. So this positive tells potential energy is stored. This negative tells the potential energy is lost. Now, coming to the next one, potential. It is simply when I make this charge as unity. So, it is work done by the unit positive charge in moving from infinity to any point inside the field of the other charge or a system of charge. So, if I relate the potential and potential energy, potential is U by Q, and if I consider the case which I was already taking as equation number 3, if I call it as K capital Q small q upon R divided by Q cancels and it gives KQ upon R. And what we are seeing when I say it is potential, it is a single charge. That means this charge has the potential V at a point R, at a distance R. So we can say, depending upon what is the sign on the charge, potential will also have either a positive value or a negative value. Potential is work done by unit charge. Work is a scalar quantity, charge is a scalar quantity. So potential is also a scalar quantity. It depends upon what is the charge and what is the distance in the present case. It can have positive, it can have negative values. Again, I am repeating it. The potential energy can also be given as QV. What is the difference? As I have earlier told, the force is equal to QE. And now we have studied a lot in details. E is not always KQ by R square. Depending upon line charge, sheet charge, spherical charge, it can have different expressions. So, force remains same as Q into E. When you bring a charge in the field, E will have experience the force QE. Exactly the same way, whether it is a system of charge, whether it is a point charge, whatever it is, if the system has got a potential V, then a charge Q, when it moves under this potential difference or potential, will the will attain the potential energy given by QV. Now I go ahead with a system of point charges. That means I have taken a charge Q1, Q2, Q3, Q4. 2 are positive, these 2 are negative, and I want to find the potential at point P. As I said, potential is a scalar quantity, hence dealing with such situation is very easy. If I know the distance R1, R2, R3 and R4, the potential at a point P will be KQ1 by R1 plus KQ2 by R2 minus, because it is a minus sign here, minus KQ3 by R3, and this is also a minus sign, and hence it is minus KQ4 by R4, and that is what is the total potential due to all 4 charges at this point. So, if at that point P a charge capital Q is placed, then simply by multiplying this Q with V, we can find out what will be the potential energy. So, this was the expression for potential due to that system of charge. If I multiply it with Q, that is the total potential energy of the charge Q. Now, if I say there are 4 charges, then I can think about 2 types of situation. I can talk about like this, what is the potential energy possessed by this charge, then I can give the expression simply like this. But if I say there are 4 charges like this, and what is the total potential energy of the system? Now, what this question says? This says that because this charge is present, it has its own field. In order to bring it, there will be certain work done. That will store certain energy. Similarly, this one and this one also. That means if we talk about whole system, then it will be the whole of the energy possessed by individual charges due to some other's field. So, now I have to consider all the pairs, and hence I will be getting, let me start with the first pair, let's call it as the Q minus Q1 plus Q2, and this distance is R12. So potential energy will be minus K Q1 Q2 upon R12. If I talk about the next one as the distance R13 like this is negative, this is again positive. So minus K Q1 Q3 upon R13. Here it is minus, and this is also minus. Minus minus becomes plus. KQ1 Q4 R14. Now this does not complete. This is only with respect to one charge. There are another charges also, like this 2, and so on. So we have to consider that pair also. So the next pair, if I talk about, this is positive, this is also positive, will give rise to a positive, and the distance between these two is 2, 3. So KQ2 Q3 upon R23. KQ2 and Q4, now it is negative. So it will give rise to a negative value upon R24. What is left? In this one I have not tackled yet. So let me tackle it here, and I call it as minus K Q3 Q4 upon R34. So now this has become the total energy of the system. If I give, it was the example with only 4 charges, it can be any number of charges. So if I write it in terms of a very general term as sigma I 1 to n, j also varies from 1 to n, then it will be the due to the charges k, qi, qj upon and their distances rij. Obviously, a charge q2 cannot have potential energy due to its own field. So naturally, I cannot think about I is equal to j. So the term I not equal to j. You can see here I have multiplied with 1 by 2. Reason, when I say ij, it is for some time 1 and another, this is 2. Next case will be this is 2 and this is 1. And you can observe over here, when I have taken 1, 2, I did not take 2, 1. That means once I have taken R1, 2, I did not take R2, 1. I cannot take the same thing 2 times. But this general formula will actually summate all twice. In order to eliminate that situation, it is 1 by 2. So, the potential energy of the system will be an expression like this, and we can compare it with here considering only 4. That you can do yourself. Now, in my previous lecture, number 10, we have discussed the potential energy of a dipole. It is placed in the external uniform field. This is the uniform field, we have studied it, parallel lines. And this was a general case of putting the dipole minus q plus q over here. And we have done, in such case, the potential energy of the dipole is minus Pe cos theta. At that time, we have not studied the concept of potential, that's why we have not dealt in details. But soon we talk about the electric field, we relate it with potential. So first study that, then I'll come back to this point. Relation between the field and potential. For a point charge, field is kq by r square and potential is kq by r. If you see directly, there is simply a relation of r square and r difference over here. That means if I say v by r, it is E. Although I will not say like that, because depending upon situation, it can have a variation from one point to another point. So directly total potential upon total R, I cannot answer like that. We have done earlier, U is equal to W is equal to minus F dot dr. Now this we have studied. U potential energy can be given as QV, force is QE. Just for your revision, I have written over here U is equal to QV and F is equal to QE. If I put it over here, V comes out to be minus integral of E dot dr. Very important expression, remember it. Similarly, if I talk about the work done, dW is equal to F dot dr, and when I talk about potential energy, du is equal to minus F dot dr. From here I can say F is equal to minus du by dr. Again, another very important relation between the force and potential energy. Force is negative gradient of potential energy, or as we have earlier also done, work done is integral of F dot dr. And when I talk about potential energy, it is minus F upon F dot dr. So again, F is equal to QE and U is equal to QV. If I put it over here, E is coming out to be minus dV by dr. E is equal to minus dV by dr. Another very important relation between E and V. Observe here, negative sign. What this negative sign says? This says that when we move along the direction of field is a vector quantity, it has got a particular direction. That means if you go along the direction of the field, then what is this? dV means change in the potential. What is this dr? Change in the position. When you go along the field, this negative sign says that the later one is smaller. That means the potential drops. So I'll again put it in a sentence so that it is simple to understand now. When we move along the field, the potential drops. Simplest. If I take this example, if you move along the field, potential here will be less and here will be more. That's what I have written over here. V2 is less than V1 from this figure. And because it is uniform field, naturally potential at all the points in this line will be same. Similarly, all the points on this line will be same, because any line if you take, it is the direction of field we are talking about. So any point, if I talk about this point, it has got a potential V1. This point has a potential V2, same as the potential here. It is same. Now this charge minus Q is in the potential V1. So how much will be potential energy of it? It will be minus Q V1. What about potential energy of this plus Q charge? It will be plus Q V2. So this will contribute, the positions will contribute to the potential energy. Now we have the potential as U1, which is minus QV1, U2 plus QV2, and earlier we have done it is minus P cos theta. That means total energy will be U plus U1 plus U2, which is plus QV2 minus QV1 minus P cos theta. I can write it as QV2 minus V1 minus of PV cos theta. This is the total potential energy of the system. A few minutes back, we have discussed the potential energy is equal to Q KQ by RB minus KQ by RE from this equation number 3 here. Here I have denoted KQQ 1 upon RA minus 1 upon RB if I take KQ inside. That's what I have done over here. KQ inside. Now because we have understood and studied the concept of potential, now I'll relate it as the Q KQ by RB minus KQ by RA. This talks about potential at the position RB. This talks about the potential at position RE. So I can write it as Q VB minus VA. What is this? This is the difference between potentials at B and A. This is also known as potential difference, VB minus VA. So potential energy becomes Q VB minus VA, or I can also call it as work done between A and B. This is final position, this is initial position, work done in moving from a charge small q from A to B. Another thing, this E is equal to minus dV by dr can also be given as a simple word, negative potential gradient. Field is negative of potential gradient. From here I will give one more unit of field. Earlier we were talking about field relation with force and we used to call it as F by Q. F has unit Newton, Q as Coulomb, so Newton per Coulomb. Till now we were using field as Newton per Coulomb, but after studying this is potential and this is meter. This is V and this is meter. So potential field has another unit as V by M, volt per meter. Now let's go ahead with some numericals. Let me stop the video here. I'll take up from here in the next lecture. Thank you.